G'day everyone, how's it going? And welcome to Lubricant Apprentice Technician Training. Now this is a really big deal. ICML, which is the International Council of Machinery Lubrication, they have, in their wisdom, decided that there needs to be some kind of entry-level training. So basically, the traditional path up until this point has been able to do MLA or MLT 1, that's Machinery Lubrication Analyst or Machinery Lubrication Technician, level 1, then level 2, and then for MLA, there's also level 3. However, MLA requires 24 hours of formal in-class training, whether that's online or in person. And that's a big commitment for a lot of companies. And let's say, for example, if you're someone who holds a grease gun or does occasional lubricant top-ups, maybe your business is not willing to invest that amount of time or money in order to get you trained. Now, whether they should or not is a whole different story. I think that everyone should be MLA 1 certified. But there is an argument that a kind of first rung on the ladder is needed. Now, in this particular course, I am running this online on YouTube for free. It is going to be ad supported. And so if you find, as you're going through this, you're going, oh man, there's too many ads and I wish I could skip ahead, there is going to be, in a couple of days' time, if you're watching this as it first comes out, there is going to be a member section of the YouTube channel. So if you press the button to join as a member, I think it's $30 a month or something like that. It will then give you access to a completely ad-free version. But I wanted to make this available completely free because I actually completely am bought in and believe in the vision. And the vision is that lubricants have what I would call a last mile problem. So you've probably heard of this like last mile issue with things like Amazon deliveries, where there's all of this difficult work that goes on to get a package shipped to the Amazon warehouse, and it goes through a whole bunch of distribution centers, and there is this last mile issue, which is literally taking the package from the local distribution center to your house. That's considered the last mile problem. And the last mile problem in lubricants is the distance between basically the lube room, the lube shed, and the gearbox. And that's where so much damage happens because the person who's holding the grease gun or is doing the lubricant top up or is taking the oil sample is often the least trained person in the plant. And that's a real shame. There is just this lack of awareness for how lubricants should be treated and how they should be maintained. And that's what we're trying to really solve with this course. So let's not waste any time and let's get into what we are going to call Lubricant Apprentice Technician Training. Now, as I go through these materials, right, I am occasionally going to need to pause and I might try and draw something on the screen. Obviously, this is, let's call it semi-interactive, right? So there is an opportunity for you to comment below the videos if you're watching on YouTube. But this is an introduction to Lubricant Apprentice Technician Training. And like I said, this is entry level. So we are expecting anyone who is interacting with lubricants on a day-to-day basis. So if you run a lube route, if you have to do occasional top-ups, if you hold a grease gun, if you take an oil sample, this is for you. Right, so I'm thinking that this should apply to lubricant technicians, fitters, mechanics, even some boilermakers, as well as electricians who often are, regreasing electric motors. This is, for you guys. All right, so let's get started. And I'm going to skip over this, which is my introduction page. Basically, I am, I would say, relatively well credentialed within the industry. I have done a fair bit of work across all sorts of parts of industry. But the main thing that you need to know from me is, like most people, I did not intend to become a lubrication specialist. This is not something that is kind of like a labor of love, right? People don't get into this business because they dreamed of becoming a lubrication specialist. They get into this business because they kind of fell into it. Occasionally you'll meet people for whom it's a family business. Maybe their father was in the business and they've inherited the business. But most people fall into it. And then typically people then fall in love with it, right? So I personally, for example, was working as a drilling engineer, so I used to drill gas wells for a living. And by a series of personal circumstances, I ended up in the lubricants industry. And now I just love it. I love everything about it. I think the role that we play is so essential to the modern economy that I would not want to have it any other way. So, without further ado, let me present the science of tribology. So, what we do actually exists as a small part of a much larger world. Tribology is the study of friction, wear, lubrication, and interacting surfaces. So it goes well beyond just liquid and lubricants and greases. Think about, the interaction of tires with a road. That's an instance where you want high friction, right? High friction is desirable in that circumstance. What about the design of brake pads and brake calipers? That's all about maximizing friction with minimal brake fade. Okay, so that's an area that we want to explore. What about the design of things like biotribology? So that's things like implants. The human shoulder joint, for example, is only really designed to last one lifetime, and even then, sometimes it doesn't make it to the finish line. So how can we design artificial joints that are supposed to perform for long periods of time? And the way that I really describe this kind of field is it's a mix of different disciplines. Most people come at this from either the mechanical or the chemical side. So you'll meet a lot of oil formulators, the people who put together the actual products themselves, and they will come from some kind of chemical background. Maybe they're a chemist or an industrial chemist, and they need to learn the mechanical side of things. They need to understand better the gearbox that their products will go into, or the hydraulic pack. Right? On the other hand, there's a lot of us, myself included, who come from the mechanical side. So I'm a mechanical engineer by training. I worked effectively as a mechanical engineer for a long time, and I needed to learn the chemistry side. I'd done some basic chemistry as a high schooler, but frankly, I was never really good at it. And so learning the chemistry side and how it interacts with things like machine surfaces is really important. And then there is a certain extent of it's just MacGyvering it, right? Just making it up as you go along. And although I say making it up as you go along, this is really what I'm talking about is experience, right? It's people who spent so long in the field that they know what the bearing needs. They can look at a gearbox and intuit, yeah, that's probably an ISO 320. That kind of retention of institutional knowledge is something that we're frankly losing at the moment. And it's one of the reasons this training is so important. So, without further ado, let's discuss exactly how lubricants work. And this is one of those things where maybe you haven't really thought about how lubricants work in detail. So let's cover it, right? Let's talk about this thing called the Stribeck curve. It sounds like a technical name. Don't worry about the name. Just concentrate on the image. I want you to imagine someone who's trying to move a block on the ground. Simple, very, very, very simple mechanic. So a person comes along and wants to push it. And humans in general are pretty lazy. I know I am. So we want to use minimal effort. How can we reduce the amount of effort required to move that block? We've got a couple of levers we can pull. The first is, what if we change the ground? So rather than it being, let's say, a dirt road or asphalt, what if it's a polished concrete floor? Right, so very, very smooth. The kind of thing that you would see inside of a very fancy house or a industrial warehouse space that's been converted into a cafe, right? That very, very, very slick kind of concrete. That would reduce the friction. Alternatively, we could mess with the surface finish of the block itself. Maybe we coat the block in Teflon, as an example, to reduce the friction. Now, I want you to imagine that we could lay a very, very thin film of liquid lubricant on the floor, because that should, in theory, help us, right? Anyone who's slipped over on a workshop floor, which has a bit of residual grease or oil, will understand how slippery it can be. So, now let's look at how much effort is required. So initially, one thing that might be a bit counterintuitive is if I'm plotting coefficient of friction, so that's CF, against the speed of the block V. Now, initially, if we're able to get a little bit of movement, And so we're picking up a little bit of speed. This might not make a lot of sense, but the actual coefficient of friction will stay constant because the coefficient of friction it's actually dictated, really, if I can try to draw this out a little bit or point to it, it's really governed by the interaction between the block and the ground. That interaction, as well as the actual load of the block, so how heavy it is fully determining the amount of friction. Now, what happens is that we may increase the speed, and what we will typically see is a huge reduction in friction. Now, why is that? We're getting separation between the block and the ground. You can think of it in a couple of different ways, so I like to give a few analogies here. Anyone who has lost control of their car in the wet. So you're driving, and remember, we have high friction in the contact between the tires and the road. All of a sudden, we hit a patch of water, and there is a disconnection. So we are aquaplaning now. So the tire is skimming across the surface of the water instead of the surface of the road. So the friction is now a fluid to solid interaction. So it greatly reduces the friction. The other way that you can think of this, and why would the block rise? Think of a boat on a lake, and it sits low in the water at very slow speeds, and as it gathers speed, right, the boat rises up in the water. So it rises up, the block rises, and as a result, the friction, instead of being between the block and the ground, is now between the block and the liquid. So we get huge reductions in friction. Now, if I continue to increase the speed, what do you think is going to happen? The friction goes up, down, stays the same? Well, in practice, as we continue to increase the speed, the friction will now start to climb. Not to the same point as where it was before when we had solid-to-solid interaction. But again, going back to the boat analogy, it's like now if I slam on the throttle and the boat continues to pick up speed, for every unit of speed that I increase, now I have to push more volume of water out of the way per unit time. So the water is trying to resist my motion. And that's what's causing an increase in relative friction as I increase the speed. So we now have all of the elements of something which is called the Stribeck curve. And up until this point, we've just been talking about speed, but actually on the x-axis, we could put load, viscosity, and speed. And it gives us this kind of formulation. Now, on the left, right, that's this area under what we call boundary lubrication. This area of boundary lubrication, which you might be able to see, right? We are, hang on a sec, I'm just going to pause this. Pause. All right, so now I'm going to see if I can draw here. So the first thing is that I want to do over here, right? So this area, right, under the blue line over here. This area is what we call boundary lubrication. And so you can think of this as the metal on metal. So if we had two gear teeth, as an example, right, those gear teeth would be rubbing against each other. Think of this area here, right, under this boundary lubrication line. Think of this as relating to slow speed and high load. So slow speed, high load. Now over here, in this area here, hydrodynamic lubrication. How should we think of this? This is the opposite, right? This is high speed, low load assets. And the thing with hydrodynamic, as it sort of is implied by the name, is we've got complete separation. So actually, in an ideal world, the gear teeth should never touch each other. So as they slide past each other, right, then actually there is the metal surface and then a liquid lubricant film which separates the surfaces and then another surface, and they never touch, right? That's the objective. And what gives us that? It's the viscosity. Right? The viscosity of the lubricant helps to separate those surfaces. And then that's the reason they never touch. So that's called hydrodynamic. And basically there's a transition in between, right? Where you've got to go from full metal contact to no metal contact, and that's called the mixed lubrication regime. All right. So if we continue on in our journey, that now starts to talk to different kinds of lubrication. I want you to imagine a plane bearing. All right, so plane is, a circle inside of another circle. A crank pin and a bushing, right? Would be a classic example. The pin on the bucket of an excavator, right? Even a gas or a steam turbine. Hydrodynamic lubrication, which is on the right, is what we call kind of full film lubrication. And what you can see here, right, is that this rotation, right? So the asset itself is rotating, it's spinning. And what that causes is as the lubricant forms in here, right? So as it gets sucked into this load zone, what happens is it forms a wedge, and the lubricant increases in pressure, and it helps to separate those surfaces against each other. And then the fluid comes out the other side here, and it reduces in pressure. The other way that you can think of this is, I don't know if you've ever been in a pool and held a ball and spun it really quickly. The spinning ball will actually rise up in the fluid, right? So it'll generate what we call its own lift, its own hydrodynamic lift. And so actually, when this spins, it starts to self-center itself, right? And that's part of what gives us that separation. All right, so that's hydrodynamic lubrication. And in a lot of assets, this is where we want basically a spinning shaft to spend the vast majority of its life, because it's minimal friction, minimal wear. Now let's go over to the other side. What about this boundary lubrication? What is that? So it's the opposite. Think of very high load, slow speed kinds of things. So the classic example that I always give is the pin on the bucket of an excavator, right? In mining or construction equipment. You think about that bucket, it's moving from this to this. It never even makes a full rotation over the course of its life. And it's picking up immense loads. Some of the buckets or the shovels that you see on mining equipment is carrying many, many tons of ore. So that movement, right, is slow. It experiences high load, and it doesn't do a full rotation. So it's actually moving between zero speed, full speed, and zero speed again, right? So that movement, in the way that it's motivated, means that ultimately we will never get complete separation of those surfaces. And so down here, right, what you generally will find down here is that you get metal to metal contact. And that's where you experience the most friction and the most wear. Now, we have other tools to be able to overcome that, which we'll talk about in a second. But boundary lubrication is realistically, you're going to get metals grinding on other metals. All right. Now let's look at the middle. Let's say, for example, that I have a plain bearing, and this bearing is huge. And realistically, I cannot afford for it to spend a lot of time in this boundary lubrication regime, because maybe there's so much load that the two could very much weld together. I don't want that. But at the same time, I need to start up the asset. So at zero speed, remember, we can't do this, right? Because this here, hydrodynamic, dynamic means I need speed to get it. So hydrostatic is, well, how do I get separation when I've got no speed to play with? This is very common on things like mill bearings, so like trunnion bearings. We see it a lot in steam and gas turbines. So if you're familiar, there'll be a jacking oil system, which will effectively use static fluid pressure. So we are going to exert fluid pressure underneath the bearing to lift it up, and then we will start the motion. So we have that full separation. Now we start motion, and then when it starts rotating, and eventually at a certain speed, it will move into this hydrodynamic regime, and we can turn off the jacking oil pumps, right? Because now this separation of the surfaces will continue because of the rotation and the speed. Right, so boundary, hydrostatic, and hydrodynamic. And these are fundamental, right? These are absolutely fundamental to the concepts of lubrication. So, what's next? Hydrodynamic and elastohydrodynamic. And I promise this is going to be the biggest word that we do in this entire course. So hydrodynamic lubrication is what we've just talked about. And then it has like a cousin called elastohydrodynamic lubrication. The easiest way to break this down is that if you look at these two surfaces here, right? I said it's a circle inside of another circle. So realistically, what this is saying is that these two shapes run parallel to each other. Right? The shapes are the same. They run parallel to each other. Here, on the other hand, they don't, because you can see that this radius here is substantially smaller than the radius of the outer race. Now, you might say, well, seems like an arbitrary difference, right? Why do we care that there's a difference between these two? But it fundamentally changes the motion, because here you can see that one surface is sliding relative to the other, whereas here this is going to roll relative to the outer race. Hence the term rolling element bearing, right? So it's because this one here, it rolls, whereas this one slides. Okay. Now, again, you might think that, well, why do we need to distinguish between the two? Well, actually, the motion of those is going to dictate things like how do these components wear. Something that rolls will experience more fatigue, whereas something that slides will experience more abrasive wear. So you can imagine that if we had a sort of like a small contaminant, right, as an example. So if we got a little contaminant in here or in here, in the elastohydrodynamic case, if I roll over a contaminant, it's like hitting a speed bump in my car, but I didn't press the brake beforehand. I didn't slow down. So as it quickly rolls over this bump, or it's like hitting a rock when you're riding a bike, boom, it's this sudden impact. And you feel it, like it goes through the shock absorbers in the car. You know, the structure of the car feels it when you really hit a bump very, very hard. Or, you know, you hit a large rock when you're doing some off-roading. So that continuous shock is going to cause fatigue wear. It's going to cause cracking eventually, right? Whereas here, you can see that this particular particle is going to get dragged through, right? That's the motion that will happen to a particle in there. And so it's more abrasive. It's kind of like sandpaper, right? It's grinding away at these surfaces. So the way that these bearings would fail will change. So elastohydrodynamic, remember, this here is when the surfaces are not the same shape. So think rolling element bearings, cams, and gears. On the other side, these are the same shape. So think of Kingsbury bearings, think of engine bearings, think of plane bearings, and slideways, right? So linear bearings. All right. So now that we've covered that, let's return back to our what we call the Stribeck curve, and let's give a bit of a summary, right? So effectively, what we're saying is, remember, at boundary lubrication, it's low speed, high load. For hydrodynamic lubrication, it's high speed, low load. And another reason why this is important to make these distinctions is because now we can very clearly see that, let's say, for example, in this area for boundary lubrication, it's the additives which are going to be so important to the performance of the lubricant. Whereas over here in hydrodynamic, it is going to be the base oil. And we're going to get on to the difference between base oil and additives in a second. All right. The next thing that I want to impress on you is, what's the size of this lubricant film that I keep talking about? Well, here's some typical oil film thicknesses. The numbers themselves are not really that important. What you need to know is hair, and you can see here that I'm no expert when it comes to hair. Hair is about 75 microns wide. White blood cells are about 25 microns wide. So you can see hair, but you can't see a white blood cell, right? So somewhere in between those two ranges, somewhere in between here is the limit of what the human eye can see. Now look over on the left on that table. All of those numbers, for the most part, are less. So what does that tell you? It tells you that the lubricant film that is protecting your equipment is smaller than the human eye can see. Now, this is where I like to kind of pause a little bit and kind of impress upon people the importance of this number, because we tend to think of lubricants as being a bit of a blunt instrument, right? We pour them in, we pour them out of the bottle, right? Let's say, for example, I've got a bottle of Mobil 1 here, and I've got a bottle, another Mobil 1 bottle here. This is not sponsored by Mobil, by the way, I just happen to have them. Synthetic gear lube. If I pour these two out, they kind of look the same. They smell a little bit different, right? You start to smell the differences between oils, but they're not too dissimilar from each other. They're the same color. They're roughly, right, similar kind of thickness or viscosity or consistency. So we tend to think of these products as being blunt instruments, right? Oh, it's fine as long as it's got oil in it. It's fine as long as it's got grease in it. Doesn't matter what type. But the thing I'm trying to impress upon you is I want you to imagine a steam turbine. So a steam turbine might be 50 tons of rotating steel rotating at a couple of thousand RPM. Huge load, high speed, and the only thing that is protecting it from complete and utter catastrophic failure is a lubricant film that is so small that if you cut the steam turbine, had a cross section, that the film would be invisible to the human eye. That to me is extraordinary, right? I think Castrol's got the best tagline in our business. They say, it's not oils, it's liquid engineering, right? Now, obviously, that's applicable for all brands. It's not just unique to Castrol, but I think that really encapsulates the essence of what our business is all about. They don't seem like precision engineered parts, but the oil is as precise as any other component inside of the system, and we need to treat it with the respect that it deserves. All right, so going back to this point, right, now we can start to talk about lubricants themselves. What do they do? We've already talked about reducing friction and reducing wear. Right? That is, in many ways, two sides of the same coin. Right? So effectively what we're saying is, maybe I can draw these out a little bit. So the idea here is, if I've got let's say I've got two surfaces, right? Now, the thing is, no machine surface, when you zoom in, is perfectly smooth. They will typically have some kind of roughness to them. And the idea of lubricants, the primary purpose of a lubricant, is to make sure that we have sufficient separation between these such that the lubricant completely separates them. Right? This is a terribly crude drawing, by the way. So the idea is, if these peaks, which we call asperities, right? The peaks, if they come into contact with each other, that's where the wear is going to happen. And so it is the job of the oil to keep them as separated as possible. And in doing so, we reduce metal-to-metal contact, which reduces friction, and it reduces wear at the same time. So you kind of get a double bang for your buck, right? What about prevention of corrosion? Prevention of corrosion is an interesting one because almost by definition, if something is coated in oil, it is not coated in water. So water is the enemy of metals as far as corrosive behavior goes. So the more we can prevent water coming into contact with with metals, the better. Okay. We also have anti-corrosion and rust inhibitors and things like that in the oil. We'll talk about them in a second. Okay, what about remove heat? Removal of heat is an interesting one. We don't necessarily think of this as being that important in terms of lubricant functions, but it really is. I want you to imagine an internal combustion engine that is running on natural gas. So there are quite a lot of these. Back in the early 2000s, a lot of people converted taxis to run on compressed natural gas. You've also got, in power generation, there's a lot of large 1 to 4 megawatt engines that run on natural gas. The flame temperature of methane actually exceeds the melting point of aluminium. So in theory, right, if it weren't for the lubricant, all the pistons, basically, if they're made from aluminium, should melt. It is the constant firing of oil at the underside of the piston crown which cools that piston and enables it to survive. Another way of looking at it as well is if you look at aircraft turbines. The oil reservoir on an aircraft turbine is exceedingly small because you pay a weight penalty, right, for taking large volumes of liquid up in the air. And yet, even with a tiny oil sump, basically 90% of the job of a jet turbine oil is to pull heat away from the bearings. So actually, the way that the oil circuit works is it goes through the turbine, pulls heat away from the bearing, and then effectively dumps that heat into the fuel system. Right, so it sort of primes the fuel because the warmer the fuel is, the more efficient the ignition. So that is one of the primary functions of a lubricant. We don't necessarily think of it that way. All right, what about removing contaminants? Yeah, this is a bit of a double-edged sword, right? So if the oil itself is contaminated, it's going to bring those contaminants to the pump or the bearing or the gears. But at the same time, we can use fluid velocity to flush contaminants away. All right. What about transmit fluid power? Well, that's hydraulic oils. We'll come to them in a second. All right. We also have, in the same way that you probably learnt about, states of matter when you were in high school or primary school, probably. Water is ice, liquid water, or steam, solid, liquid, gas. Lubricants are the same. We have solid lubricants, liquid lubricants, and technically there are air bearings. We don't tend to talk about them much because they're not very common in industry. But also we have this fourth, which is a cohesive lubricant. It's not quite a liquid. It's not quite a solid. It's a grease. Right? So that's a cohesive lubricant. And when it comes to lubricants, what are they made from? Well, they're just base oils and additives. Actually relatively simple right now. The chemistry themselves is a bit more complicated. You don't need to know the details of the chemistry. What you need to know is it's mostly base oil and additive. Additives are kind of like the KFC's 11 secret herbs and spices, right? They're sort of a, what's that? The Salt Bay meme, right? Of sprinkling golden flakes on a steak. That's kind of the way I view additives, right? It's the secret sauce of our world. But the base oil, for the most part, does the heavy lifting. And depending on what the application is, the proportion of additive will be more or less. So marine engine oils, for example, are the most heavily additized. You're probably looking at like 20% additive. Compressor and turbine oils, barely any additive in them. So what is this base oil and why is it so important? Well, base oils can actually come from effectively three different sources. They're natural, they're mineral, or they're synthetic. And you've probably heard the terms before. So natural, what is a natural product? A natural product is kind of like the vegetable oils, right? So where do vegetable oils come from? They're seed oils. They've gotten a bad rap lately for health reasons. There's seed oils or fruit or fruit oils. So think of olive oil, right? So it's the fruit of an olive tree which is pressed. There are things like rapeseed oils, beans. We squeeze castor beans, for example, to make some of the world's oldest lubricants, which are actually still commonly used in greases today. So castor beans, if you press them, you get castor oil. And if you're from the UK, you would pronounce that castor oil, hence the name Castrol, right? So natural products. These are still actually relatively common where we need lubricants that are kind of edible. Note that is not the same as food grade for anyone who's working in food manufacturing. So edible products, sometimes biodegradable products will be made from natural sources too. All right, what about the minerals and synthetics? So mineral just means it's from rocks, whereas synthetics means we manufactured it. So when I say mineral from rocks, that's like the vast majority of the base oil volume. And the way that I tend to think of it, right, is that oil comes out of the ground and therefore it is a natural product. It's formed by natural processes, which are the breakdown of organic natural materials. Now natural often has connotations of better, healthier, right? In our world, for the purposes of refining and manufacturing, natural means more unorganized, more random. So when a barrel of crude oil comes out of the ground, it's a mix of all sorts of different stuff, some of which we don't want and some of which we don't. So a very simplistic way of thinking about it would be that a barrel of crude oil is like a box of Lego. So everyone has that box of Lego, which is a box of Lego. So you make the Lego creations, and then eventually everything gets broken down and put into the one giant box. That's a barrel of crude oil. And the exercise of refining is, can we sort out those pieces, right? We make different things out of different pieces. And that's why mineral oils are very easy to come by, because we produce so much crude oil, but also why they have, let's say, not poor properties, but less than ideal properties, is because that refining process is never perfect. And this helps us distinguish between that and a synthetic oil, right? Where a synthetic oil is the case where I have made, using exactly the same Lego brick, I have made the structure that I want. Right, so that's the difference between a mineral and a synthetic, and it's why synthetics tend to have better properties. What kinds of properties? Well, sometimes they flow better at cold temperatures. Sometimes they're more stable at high temperatures. Sometimes we want them to look a little bit like antioxidants. Sometimes we want them to be very ordered and low friction. So there's all sorts of reasons why we might want synthetics, right? And there are many types of synthetics as well. We don't need to get into the details of all of them, but probably the three which are most, well, actually, let's go through the ones which are most noteworthy. So PAOs up the top, these represent the vast majority of synthetics. They separate very well from water and air, and they can last a really long time. The polyglycols or polyalkylene glycols are fantastic lubricants, great traction coefficient properties, very good lubricity. Unfortunately, they don't like to play nice with the other lubricants, so they often running you into compatibility issues. The esters, also really good lubricants, very stable at high temperatures. The jet turbine oils, for example, are commonly made from polyol esters, as are some of the fire-resistant fluids. However, their weakness is water. The phosphate esters, kind of a similar deal. They're flame, they are fire resistant in a lot of cases, right? And that's why they're desirable. However, again, they're prone to this thing called hydrolysis, which is that water can make them weak. All right. Now we're going to move on to the properties of lubricants that you really need to know. And what do you think are the three most important properties of lubricant? I'll give you a moment. All right, the three most important properties of a lubricant are viscosity. You might have already guessed that. But also number 2 and number 3, also viscosity. And I'm not just saying that to be a smart aleck, right? I genuinely believe that the bulk viscosity of a lubricant is the most important property, followed by viscosity's relationship with temperature and viscosity's relationship with pressure. So what do we mean by viscosity, right? First of all, we can think of it as just being thickness. Water's thin, honey's thick. I think that's pretty obvious. Alternatively, we can think of it as the resistance to flow. Water flows easily, honey not so much. But that also sounds a lot like back pressure. So actually, if we change the viscosity of oil in a line, it will often cause the pressure to increase because it increases resistance. And the formal definition is the resistance of fluid to an imposed shear force. So what does viscosity do? It separates these surfaces. Right? The thickness of the oil gives us that separation. So more viscosity means more protection. So that begs the question. If more viscosity means more protection, and I want to protect my assets as much as possible, why isn't everything an ISO 1000 gear oil? Right? And it's because we pay a penalty. right? So once we have separation between those surfaces, I've accomplished my goal. They're not rubbing against each other. We don't have wear. We have relatively low friction. From that point forwards, if I increase viscosity, I will actually get more separation, but I pay for it with energy consumption. Because the thicker an oil is, the more energy it requires to move it around the system, to pump it, to move it out of the way. It's like putting, molasses in a gearbox. It takes a lot of effort to actually move the fluid itself. So the whole point of lubricant selection, especially when it comes to viscosity, is we want enough viscosity to separate those surfaces, and in an ideal world, no more. Right? So there is kind of like an optimal Goldilocks zone, if you will. All right, so going back to this separation is what we call the film thickness. And you don't need to know specifically how to calculate that or anything like that, right? That's done well in advance by tribologists and people employed by the OEMs. Just know that this film thickness is what is governing that separation. Now, viscosity grades themselves are measured in many different ways. The ones that you're probably most familiar with are these things called the SAE crankcase grades. So you'd see that on engine oils. So let's get my engine oil back out again. This one here, as you can see, right? This one says on the bottle 5W30. And that's probably a pretty familiar sight to a lot of you, right? For something like 5W30 or 15W40 for a diesel engine oil, these are common, what we call engine oil grades. Whereas the gear oil, just to get it out again. Sorry for the close-up of my head there. This one here, 75W90, right? That's a pretty typical gear oil grade. Now, just the numbers themselves, right? 75 and 90 are much bigger than 5 and 30. So the implication there is that the gear oil is much thicker than the engine oil. Not necessarily the case, right? So if you look at this chart, you can see that an SAE 90 gear oil is about the same as an SAE 50 engine oil. We've actually got two separate but different naming conventions for viscosity of engine and gear oils. You might say, well, why? You can see here that the engine oils are numbered 60 and less. On the gear oils, I've actually got a couple missing here, but they're basically 65 and up. The idea was that in an automotive workshop, if I see anything which is 65 or over, it must be a gear oil. Anything which is 60 or below must be an engine oil. So it would eliminate the possibility of cross-contamination. All right, if you're in the industrial world, the ones that you see most commonly are these things called the ISO viscosity grades. ISO VG, so ISO viscosity grade, are those numbers where you'll see 32 is a very typical turbine oil. 46 and 68 is a very typical hydraulic oil. 46 and 68 also very common air compressor grades. What about 220, 320 is typically a gear oil, right? That's the ISO viscosity grades. And this one here, the AGMA grade. What on earth is that? AGMA stands for the American Gear Manufacturers Association. It is technically a defunct standard now. And the reason for that is because it was redundant. You can see here, a 1 is the same as an ISO 46. A 2 is the same as an ISO 68. A 3 is the same as an ISO 100, and so on and so on and so on. I just put it here because sometimes you'll see on some old nameplates, right, these AGMA grades. All right, let's keep going. Basically, as we said before, the heavier the load is, the more viscosity I need. And that's why things which are lightly loaded and fast speed tend to require low viscosity. Things which are very heavily loaded and slow speed require higher viscosity. I mean, the thickest oil that I think I've ever seen is an ISO 46000. It's so thick that you actually need, I don't know if you're familiar with Formula One, but those tire blankets that they have to heat up the tires, you need that, but for an oil drum. Right, so you heat up the oil in order to just pump it out of the drum. It's that thick. So that's your open gear oil grades. Now for the engine oils, remember I said that there's that different naming convention. There's usually two numbers, right? So a diesel engine oil will say something W something, right? The W, some people think it stands for weight. It actually stands for winter. So winter tells you the cold temperature performance. The second number tells you the operating temperature performance. So you can think of this as basically the first number with the W is how well will it flow at cold temperatures or on a cold startup. Whereas the other number tells you the amount of protection that you get once you are up at highway speeds. Right. So that's basically how that works. And again, the more heavily loaded, the more viscosity you need. All right. Now, how about how are lubricants made? There's base oils and there's additives, but there is this kind of idea that, as long as I mix the same oils and the same additives, I'll get the same product. Not so, right? The analogy that I always give here is cupcakes, right? So I've got a 9-year-old daughter, and sometimes she likes to bake cupcakes, especially on the weekend. And you would think that cupcakes are pretty simple, right? You take flour, you take sugar, you take some milk, eggs, you mix them together, you put them in the oven to bake them. It's pretty simple, right? There's a bit of icing sugar that goes on afterwards, coloring. But I can assure you that if you give the same ingredients and instructions to me and to, Chef Gordon Ramsay, or frankly, my daughter's Nana, the results will be remarkably different, right? My cupcakes never just turn out right. They're always a bit goopy. They never look right. They're always a bit lopsided. The icing never seems to hold right versus restaurant quality. And it's the same ingredients. So it's the manufacturing process and the manufacturing expertise which make the difference. And this is why there is an argument to be made for making sure that your lubricant supplier is of high quality, right? Because it's not just the ingredients that matter. It's not just the ingredients that they're buying. It is the quality of the manufacturing process. So how does manufacturing process affect the quality of a lubricant? Well, some of the additives, for example, need to be heated as they are mixed. Some might need to be mixed with a high shear rate. That's the equivalent of using like a kitchen mixer, right, to whip up cream or something like that, right? So that sort of manufacturing expertise plays a role in lubricant quality as well. What about those additives though? Because we've mentioned additives a couple of times now. They seem a bit sort of pesky, maybe. What do they fundamentally do? Well, the good news is for us is that lubricant additives. My industry, we are some of the most deeply, how shall I say this? Deeply uncreative people in the world. So fortunately, when we name something, it's just what it does, right? So let's take a look at some of the additives as an example. So what do you think a pour point depressant does? So first, we need to answer, what is the pour point? So you will notice, right, if you pour oil out of a bottle, right? So you're pouring it, and the temperature starts to decrease. The oil gets thicker and thicker, and it is more difficult for it to pour out of the bottle. Eventually, you get to a temperature that's so low that the oil won't pour out of the bottle. So the point at which it will no longer pour is the pour point. Now, do you think that you want a pour point that's high or low? Right? It's better for the pour point to be lower because that means it will continue to pour at a lower temperature. So you might want to depress the pour point. Hence, pour point depressant. What about, I want to improve the viscosity index? We'll talk about viscosity index in a second. Well, use viscosity index improvers. You want to swell seals? Use seal swell agents. Inhibit oxidation, deactivate metals, inhibit foam, prevent corrosion, clean, right? Prevent wear, and modify friction. Right? Again, does what it says on the tin. Now, one thing to note, we say friction modifiers instead of friction reducers. Interesting. And that's because most of the time we want to reduce friction, but not all the time. Think of clutch packs, wet brakes. These are instances where we don't want metal-to-metal action to have very low friction. So we use these friction modifiers in some cases to increase friction and in some cases to decrease friction. All right, so that's some of the additives. How can you recognize them on oil analysis? Right? Again, I wouldn't belabor this slide too much. Come back to it if you ever need to refer to it, right? So it'll help you understand that, for example, anti-wear is typically made from zinc, phosphorus, and molybdenum. EP is usually sulfur. Detergents are usually calcium and magnesium. These are the kinds of ways that we can recognize it on an oil analysis report. Okay? Now, the way that some of these additives act, it can be very complex. Right? Again, you don't need to know all the detail of this. You just need to know that there's really complex chemistry that's going on in the background. And again, this is why we need to treat our lubricants with care, because they are precision engineering instruments. So ZDDP is a fantastic antioxidant as well as anti-wear additive. We've also got stuff that acts on surfaces. Now, I just want to take one step back here, right? Because that seems all very complicated. And it's not your job to understand the ins and outs of every single additive, right? That's not what this course is all about. I'm just trying to give you an appreciation for the fact that there is a lot of science that goes into the formulation, and to not get swept up in some of the information that gets put out there by the oil companies. Sometimes you might face, for example, in the engine oil world, this idea of more additive equals more performance. And that's just simply not true. Right? So the one in particular that gets advertised a lot is zinc. So zinc anti-wear additive, zinc dialkyl dithiphosphate. And people will say, oh, I have to have more than 1,500 parts per million zinc for it to be effective or something. In some cases, that might be true, right? For classic cars with flat tappets, yeah, there's an argument for high levels of zinc. But in a lot of other cases, zinc will compete with other additives. So it might push away some of the corrosion inhibitors. Zinc itself is a little bit acidic, so you might run yourself into a corrosion issue. So more is not always better in these circumstances. So that's why you need to be a little bit careful of marketing materials, but also very careful about people who are advertising aftermarket additives. Right? So don't just go around pouring other additives into your gearbox because of some claims, right? You need to be a little bit careful of interfering with formulations. All right. What do some of these additives do? All right, so that might be a question to answer. Right? So, for example, how can we prevent wear using these additives? Well, anti-wear additives are classic. So look at this green layer here, which I'm using to represent zinc. So what they do is they interact with the top surface of the metal, and they basically form a very hard, almost glass layer over the top of the base metal. And so now when two metals come into contact with each other and rub, well, it is this glass layer that sacrifices itself and it sloughs off rather than the base metal. Right, so that's how it is preventing wear, is by kind of stacking a hard glass layer on top. We can also use solid lubricants. I mentioned that we would come back to these solid lubricants. You might have seen them in greases, graphite, molybdenum. Those greases tend to be dark or grey coloured. What about Teflon? Teflon is another classic solid lubricant. Well, how do they work? They kind of work. Maybe we should ask ourselves, how does a pencil work? Now, this might be a question that you've never really asked yourself. Like, why do I need to know how a pencil works? But the requirements for a pencil are actually very, very specific. We need a material that is very, very stable over long periods of time. But when I draw it across a piece of paper, it's a low friction, and it will also leave a trace of itself behind. That's a very, very specific set of criteria, and it's why graphite is used in pencils. So actually what happens with graphite is that if you could imagine, let's say, for example, these layers of graphite, as we are pulling it across the page, these layers are kind of sloughing off. So the key property of graphite, and then this is molybdenum disulfide, is that there are these almost like plates or these layers that are very strong themselves, but they have very little strength between them. So we say it has low shear strength. The other way that I kind of give an example is it's like trying to run on a bed of playing cards, right? So you could imagine, I don't know if you know the Looney Tunes cartoons, Roadrunner or Wile E. Coyote, trying to run on a bed of playing cards, and they're not going anywhere because the cards themselves are slipping underneath their feet. That's kind of what solid lubricants are doing for us. So let's say, for example, I had a very slow-moving plain bearing. Rather than these metals rubbing against each other, instead it's the plates that are going to move, right? So if with this rotation, the plates are sliding against each other, and that's what gives us this lower friction and lower wear, and ultimately what preserves those bearings. So that's why a lot of those mining greases contain solid lubricants. Now, an obvious question is, well, if they're so great, why don't we always use them? Like, why do we not put them in lubricants? And the main reason is because solid lubricants will settle. Right, here's an example of a Teflon fortified gear oil. After a couple of hours, it settles out. Whereas in greases, they stay suspended. The other thing that will happen is that in a lot of oil systems, we have filters. Filters are designed to remove solids. So they could potentially pull the additive out as well. Okay, so that's one of the things about solid lubricants. So you'll typically only see them in greases. Now, speaking of greases, what's the difference between an oil and a grease? It's this thing called thickener. All right, so what is the thickener? The easiest way to describe a thickener is to use the analogy of a kitchen sponge, right? So if you think of a kitchen sponge in the kitchen, what does it absorb? It absorbs water. And how does it do that? Well, just by being there, it absorbs water. How do you get rid of the water? You squeeze the sponge and the water comes out. If I want the water to reabsorb, I let go of the sponge and the water reabsorbs back into the sponge. Grease is the same. Think of the thickener as being the sponge. Now, when the bearing turns, now we're putting load on the sponge. So we're squeezing the sponge. So the oil, it comes out of the thickener, and the oil is the thing that is doing the lubricating. So the viscosity of the grease is still the most important property. And then when the bearing stops turning, we have basically, let go of the sponge again. And so the oil reabsorbs back into the sponge. Right? This is probably the best analogy that we can give. It's not perfect. People who manufacture grease will quibble with this analogy, but I find it the best way of explaining things for why grease dries out. So, and we'll get to this a little bit later, but one of the common issues that we have with the use of manual grease guns is grease constantly bleeding out. So often you'll go to pick up a grease gun and there'll be like a puddle of oil underneath the grease gun. And why is that? It's because the follower plate here is actually pushing on the cartridge of grease. So if we do not, release the pressure on the grease gun, what we are actively doing is causing that follower plate to constantly push on the grease. And as a result, the grease is actually doing its job. We are squeezing the sponge and the oil is coming out of the thickener slowly. And that's where we get grease dry out. It's the same thing for single point lubricators, right? So single point lubricators, again, often we are constantly pushing on them. And so as a result, we get dry out of grease in the lines. So things to be conscious of. So I think that analogy does a really good job of helping to explain what grease is and what it does. All right. Now, what is this thickener? Typically, it's what we call a soap. So actually, if you wanted to make grease at home, you kind of could pretty easily. Let me see. I've got some grease back here. Okay, so most grease is that kind of like, sort of. Actually, most greases are a pretty boring color when they're manufactured. They're sort of this beige color. When we make grease, where was I going with that? Oh, yes. You could make grease at home. So you could, for example, take a bar of soap and melt it down and pour in some olive oil and mix the soap and the oil, and that would make effectively a grease, right? So the soap would be holding onto the oil. And we have exactly the same thing with greases, except that the soaps are not hand soaps because we don't want them to dissolve in water. So we typically make them from some other kind of metal. And here's an example of all the different grease types. Now, the thing that you will need to know is that the vast majority of greases are made from lithium. That's like 70% of all the world's greases, lithium and lithium complex. There are other greases. Why is lithium the most commonly used? It's because lithium kind of doesn't have a weakness. Everything else has a bit of an Achilles heel. Right? There's something that those greases don't do particularly well, whereas for lithium, it does everything across the board kind of okay. Right? It's not a specialist at anything, but it's also not bad at anything. Whereas down at the bottom here, there's some kind of like specialty greases, clays, polyureas, calcium sulfonates. There's all sorts of different greases. And what is really the difference between these? Like, for example, can I mix them? Can I mix different types of greases? Is it okay to do that? The general answer to that is, I don't know. That is the honest answer. I just don't know. Because, here's the thing. If you want to mix greases, let's say, for example, you're switching between two different kinds of greases. The first thing that we would probably do is use Google. These days, you might use ChatGPT, right? But ChatGPT is going to then look at stuff on the internet. And unfortunately, there are these things called grease compatibility charts. And the grease compatibility charts, they disagree with each other. So immediately that tells you something's wrong. But also, these charts only tell you about the compatibility of the thickener. They don't tell you about the compatibility of the base oil or the additives that are in the grease either. So we need to be very careful when we are mixing greases because we just can't predict what they're going to do. Sometimes they soften, they disappear from the bearing, so the bearing doesn't have any lubricant in it and it fails. Sometimes we get the reverse and the grease hardens. That's almost just as bad because now the bearing seizes and it fails. So grease compatibility is very difficult to kind of predict. Now, having said that, right, there's a bit of fear-mongering and scaremongering. There is what I need to teach for the course, and then there's also what's practical on site, right? So are we going to, in practice, are we going to test every single grease every time we need to mix it? No, probably not. So let's use some common sense, right? So let's say, for example, I was switching between two different greases, and they are both lithium complex greases, NLGI 2, a base oil of 220 centistokes, and they're both mineral oils. Well, I'd say, and they're both EP greases. I'd say, you're in with a 95% shout that they are going to be compatible just fine. So, especially if the application is not particularly critical, it's not going to shut down the plant if anything goes wrong, I'd go ahead and just mix those two greases. But if you have a critical application and you cannot afford the downtime, you can get grease compatibility testing done. So your oil supplier should know how to do this. And basically there is a a ASTM test method by which they vary the proportions of the two greases that are going to be mixed, and then they look at how they behave. Right? So just be conscious that there is such a thing as grease compatibility testing. Now, the other thing is, right, when we are naming greases, sometimes people refer to things as the number 2 grease or the number 1. What do they mean by that? Well, this is something called the NLGI number, and it relates to basically the thickness or the consistency of the grease. Effectively, how solid is it? And actually, there are some what we call semi-fluid greases. You may have come across these, so you can tell they're semi-fluid because they basically pour out of the bottle. Right? Then we've got the standard greases. I'd say the vast majority of grease around the world is a number 2. Occasionally, you'll get a number 1 or a 3. Right? And as you go up these numbers, they get thicker and thicker and thicker. Now, keep in mind, remember, that the most important property of a grease is still the same as the most important property of the lubricant, and it's viscosity. Right? So remember, viscosity, viscosity, viscosity. So even though it might be a number 2 grease, the viscosity of the oil inside the grease is the thing that matters. Typically, you'll see electric motor greases are usually around an ISO 100. Your multi-purpose greases are an ISO 220. And heavy-duty greases might be around ISO 460. Right? That's sort of a very typical set of greases. A lot of plants will try to rationalize down to effectively 3 different greases. They might have an electric motor grease, a multi-purpose grease, and a high-temperature grease. Right? That's very typical of a lot of sites. So, anyway, that's what you need to know about grease itself. We will talk about grease application using grease guns and all that sort of stuff a little bit later on in the course. Last thing, what is complexing? You might have heard lithium versus lithium complex. Again, you don't really need to know the ins and outs and the details, but just know that a complex grease has more stability, has better physical stability. It's like putting more rungs on a ladder, right? It makes it more stable. All right. Now, what do you need to know about something like the way that viscosity changes with temperature? This is something which we call the viscosity index. Interesting one. What is viscosity index? So, if you think about if I could design the perfect lubricant for an engine, what would it do? Well, on startup, at very, very cold temperatures, I want an oil that is effectively as thin as possible, because on startup, I want the oil to flow around the engine as quickly as possible. So any component which was dry is now lubricated and protected as quickly as possible. Most of the wear in an engine actually happens on startup because the engine components are dry. But once we get up to like operating loads, I actually want the oil to get thick, because the thickness is what gives me protection, especially at high loads. Mother Nature, she's so annoying. She gives us the exact opposite of what we want. She gives us fluids which are thick when they're cold and thin when they're hot. So we want oils that will resist this as much as possible. And that's what we're referring to when we talk about the viscosity index. So we measure the viscosity at 40 degrees and 100 degrees, and then we see how much it drops off. Now, viscosity index improvers are those additives which can improve the viscosity index. And these are unique molecules which are small when they're cold and they're large when they are hot. Right? So, things which shrink when they're small, huh? I wonder what inspiration they took for those. But the basic idea is, and I use the engine oil viscosity grace to demonstrate this, if I just have an SAE 40, right, so it behaves like a 40 when it's cold and a 40 when it's hot. If I've got a 10W, that's just lowering the overall viscosity. But a 10W40 is something that acts like a 10W when it's cold and a 40 when it's hot. And you can get to this with a higher viscosity index base oil or a mineral base oil with viscosity index improvers. That's the basics of it. Again, you don't need to know a whole lot of detail. Now, how does viscosity affect things like, how do we choose an oil for a viscosity, and how does it affect things like bearings? Right, so with bearing selection, oil selection for bearings, we are usually looking at a combination of the speed, the load, and the size of the bearing when we select our oil. And we want to be actually a little bit careful about selecting our oil on things like rolling element bearings, because if we go too high, remember it's resistance. It's resistance to motion. So we want to make sure that we have enough viscosity that will separate those surfaces, but not too much that we waste energy. Similarly with engines, right? So with engines, I always use engine lubrication as an example of something that is extremely complicated, right? Because think about the different kinds of lubrication that are going on. There are plain bearings inside of the crankcase. There are linear bearings as the piston moves up and down on the liner. What about small end, right, is another plain bearing. But often you'll have needle roller bearings up here on the camshafts. You might have a very high speed bearing at the turbo. You have to deal with all of this kind of junk that is produced as a result of combustion. So it is actually very challenging, this environment. But we get to pick one single viscosity. And so, that being the case, here is a way that you can go about it. Now, most of the time, you just pick what the OEM gives you. But if you, for example, like building engines in your spare time, which a lot of people in our business tend to like to do, here is a bit of a guideline based on your bearing clearances, the materials that you are using, and the kinds of temperatures that you would run at. So, now you know more about lubricants than you probably ever thought you needed to, and so we can now answer the final boss question. What is WD-40 for? Ah, dear. It's a question I get a lot. So, why do we need WD-40? And what should we be using it for? So everyone kind of knows the law, like what is it, water dispersant or water displacement or water dispersant for attempt number 40, I think it is. But people use it as kind of everything. And sometimes you'll get people saying it is a lubricant. And their justification for it is, oh, I had a door hinge, it wasn't moving, I sprayed WD-40 at it, and now it is moving. Ergo, it's a lubricant. It lubricated. The thing is, you need to delve into it a little bit more, and you need to download the data sheet. I'm probably the only person that's ever done this, right? Is download the actual technical data sheet for WD-40. And what will you find if you see this data sheet here? What is this? Oh. It gives us the viscosity of WD-40. And the viscosity of WD-40 is 2.8 centistokes. Now, what did we say is the most important property of a lubricant? It's viscosity. And this has almost none of it. 2.8 centistokes is nothing, right? 2.8 centistokes is the kind of thing that you would use in the textiles industry for bearings that are rotating at 100,000 RPM. So this is not carrying any kind of load. And yet, it's able to free up a door hinge. So what's it doing? So effectively, what these products are doing is they are acting as a penetrating oil. So here is an example of a penetrating oil. Right, I'll see if I can sort of play the video here. Will it play? Here we go. So the idea here is that if you spray a very, very thin oil, it will be able to get into very, very small cracks and displace things like rust or corrosion products that have stopped the door from moving. And if they can shift that material away, then they will enable it to move. So you can kind of think of it as effectively a penetrating oil. That's one thing that WD-40 is fantastic for. Right. So now let's think of another circumstance. I want you to think of how do you lubricate a chain? With all this knowledge that we've accumulated, right, we're going to talk about a chain. So I'm going to, again, I'm not particularly good at drawing with this pen here, but I'm going to draw, here's the link. And here are the pins on a chain. Now, if I want to lubricate this, some chains are under relatively high load. So what does high load mean? It means I need a higher viscosity. But if I were to pour honey on this chain, right, high viscosity, it's going to be too thick to get into these very, very, very small links. Right? The gap there is very small, and so it's not going to penetrate correctly. So I need something that's thin. But that now runs counter to what we wanted, because now I need a fluid that's thin so that it can get into the link, but I need one that's thick so that it can protect. What am I supposed to do? Because they are what we call mutually incompatible requirements. I need thick and thin at the same time. All right. So unless you employ magic, we've gotten around this issue by using solid lubricants. So we can use a thin carrier fluid like a WD-40 or an aerosol spray to spray into these links, right, and carry like a Teflon or a graphite into the links, which will remain behind and help to lubricate. So that's why you see a lot of these variants on WD-40, is to accomplish a task like that. All right. Now let's move on to a slightly more practical part of our course, which is to talk about why is it important to keep our oils clean. This here on screen is probably my favorite demonstration of this. Right? It's from a company called Nippon Steel, and they didn't publish this paper until 2016. As far as case studies go, I think it's kind of the gold standard in our industry, because it is very, very rare for businesses to look at data over this long a time scale. And it's also very rare for them to work at a project over a long time period. Typically, especially in modern capitalism where we're looking quarter to quarter, people get wrapped up in projects and then people move on and institutional knowledge gets lost. But you can look at the years here. They persisted with this project from 1979 to 1991. They saw almost zero progress in the first 4 years of their project, and then it really started to take off after that. So that persistence is the key. Now, if I can impress upon you the importance of contamination control, just see this. This red line here, this is simply the number of oil filters they had on site. They're not tracking anything else. There's a lot of other work that they did, but purely tracking the number of oil filters that they had on site. And the blue line, how many oil pumps did they need to replace because of failure? And there is a incredible inverse correlation between the two. Now, correlation is not causation. It's not the same thing. However, the link between these two is so strong, it's very, very hard to ignore. So, if you ever need to justify, a contamination control project to your management, this is the study that I would use. Now, how do we measure contamination? There's this thing called the ISO cleanliness code. If you've ever seen an oil analysis report, you'll have seen 3 numbers that kind of look something like this. 20, 14, 11. And that is talking about the amount of contamination that is inside of the oil. So, for example, if I had, in these ranges, 8,000 particles greater than 4 micron, well, I'd go over here, and 8,000 is less than 10,000, more than 5,000. So the first number is 20. And I can do this for 6. 95 is less than 160. It's more than 80, therefore 14. And similarly, right, 11 particles is less than 20, more than 10, and therefore purely by coincidence, that third code will be 11. So we end up with 20, 14, 11. Now note something. These numbers are inclusive. So as they go from left to right, they generally decrease. So for example, if I had a particle that's greater than, well, let's say I had a particle that's 20 microns in size. Well, 20 is greater than 14, but it's also greater than 6 and 4. A particle that's 10 microns will be greater than 6 and greater than 4. And a particle that's 5 microns will only be greater than 4. So you can see there are always going to be more particles in this code than there are in this code and this code. Right? Now, the thing about these codes is, if you looked back at these numbers here, look at the raw limits. They double each time you go up a code by 1. They double. So what that means in practice is that the number of particles in each code goes up exponentially. So as we go from 10 to 16, it's a massive increase. But as you go from 16 all the way up to 21, now we're starting to get to unbelievable levels of contamination. 21 and beyond to something like 28 is a huge amount of contamination. Now, the thing about this is, remember I said that the human eye can't see below about 30 micron. So all of this contamination may be occurring, and the oil sample itself, it may look perfectly clear, because the damaging contaminant is actually invisible to the human eye. Right? This here is a better example, right? So I've got an oil sample here inside of a plastic bag, and it's perfectly clear. But I can guarantee you it is not perfectly clean. Clear is not the same thing as clean. Right? So that's one thing to note. Now, why does this matter? You might be saying, oh, Rafe, I get it, whatever, contaminated oils, they're bad. But how bad? Well, again, we have data. We can point to something called the asset life extension tables. So the idea here is, if I have an oil, and let's say, right, that I believe I can clean it up from a 2220 to a 1614, then the improvement in asset life that I can get is a 3.5 or 3 multiplier. So I can get 3 times more life out of a rolling element bearing if I clean it up from one code to the other. We have similar data also for hydraulics and gears, and we also have similar data for water. Now, the thing with water is just a different kind of contaminant. We don't necessarily think of it that way. And often we will be told to look for water visually. Just check that the oil is not cloudy. But the evidence shows us that most of the reduction in bearing life occurs well before the water becomes cloudy. The oil becomes cloudy. So even though an oil can appear perfectly normal, does not mean that its performance is perfectly normal. And similarly, if we reduce the amount of water, we can get huge extensions in asset life. Now, water as a contaminant, right? I think it is kind of visually sensible as to what particles will do. So particles will cause abrasion, right? If they are hard, they can cause fatigue. They can cause locking of things like valves. They will plug up filters. All of these are pretty obvious. Water less so, right? So how is water damaging? Well, water causes corrosion. Water causes a collapse in film strength because water is not a very good lubricant. Water can also damage additives, right? It can also cause vaporous cavitation. It can cause chemical attack of the oil, which is something we call hydrolysis, increases the amount of acids in the oil. And it can do funny things with viscosity. Because if you get an oil, I kind of talk about it as being a gear oil that's turned into custard. I don't know if that's ever happened to you. If you get a lot of water into things like gear oils, it will emulsify, right? And things that we know about emulsions is that the viscosity is generally higher than the two products. So if you take, so for example, like vinegar and an egg and oil. So vinegar and oil, you mix them together, you get mayonnaise. But mayonnaise is much thicker than the other two. Same with milk, for example, or cream or butter. These are all emulsions, and the thickness is very high. So water can also do funny things with viscosity as well. You would think that water, because it's very thin, would reduce viscosity, but sometimes it increases it as well and causes oil starvation. So water is a very, very, if you like, a pernicious and very dangerous contaminant. The other thing that is also a contaminant, we may not necessarily think of it, is air. So air is unusual. There are a couple of different forms of air. There's dissolved air, there's the headspace, then there is entrained air and foam. And most people think of foam as being the most dangerous because it's the visible one. In fact, foam is kind of necessary in some ways. If you have air that is trapped inside of the oil, how does it get out? It has to rise to the surface where it becomes foam, and then the foam bubble has to pop and release the air back into the headspace. So actually, all of this air here cannot escape unless there is a very, very tiny amount of foam. So people will often see foam and think, "Oh crap! I've got a problem with the oil." But in some ways, it's a natural process, right? The air here, what's going to happen to that? If it stays in here and it never rises to the surface to become foam, it will almost certainly get sucked into the pumps and cause cavitation or microdieseling. So entrained air is a much worse problem than foam. Foam, in a lot of cases, is just cosmetic. I often will coach people. You don't have a foam problem until you have a problem with your foam. That is to say, if you've got foam, that's fine. But if your foam is starting to spill out the top and it's a fall hazard, now you have a problem. Is it causing you issues with, for example, you can't see in the sight glass, right? So here's your sight glass, and all of a sudden I can't maintain the oil level control because I can't see it. Now you have a problem. Maybe the foam is problematic because it is so high that it's getting sucked into the pumps. Now you have a problem. Maybe the foam column is so high, right, that foam has started to get into the actual breather itself. Okay, you have a foam problem. So all of these things are foam problems, but until you have one of those problems, the foam is just cosmetic. Right? All right. What about where does the contaminant come from? Right, so contamination can come from a number of sources. Built in. What are built-in sources? When new equipment comes to us from the factory, it's not perfectly clean. It's got things like machining swarf in it, salt water if it's been shipped to us by sea, rust preservatives. Rust preservatives are often incompatible with lubricants, so we need to try to get them flushed out where possible. Right? We absolutely need to flush these things out. Often that's a step that's skipped, right? We're in a rush to commission the plant. Let's just skip that step. Please don't, right? You may live to regret it. So we want to make sure that we flush all of that material out. Then as we are using the machine, right, we get the formation of wear particles from abrasive wear and erosion. Those wear particles are particularly dangerous because as they circulate through the system, they get work hardened. So the longer they spend in the system, the harder and more damaging they get. Then we've got things that are the byproduct of the oil itself, sludge and varnish, which might coat bearings, reduce their ability to dissipate heat. We might get issues with valve sticking, filter plugging. What about added? Well, I mean, I know that you personally would never add the incorrect oil, right? But it happens from time to time. So incorrect oil, water from drums, we'll explain that in a second, dirt from dispensing containers, and then we've got things in part of the process, getting past seals. So all of these areas are areas where contamination can occur. Now, your site should have something like a contamination target. That's probably been developed because of, OEM manuals or something like that, right? But if your site does not have a contamination target that you are working to, ask about it. Right? This is an opportunity for development because, and I'm speaking to the audience now that's probably taking this training. If you are someone who does oil dispensing, how can you keep score? How do you know that you're doing a good job? It's by measuring whether the oil going into the unit is meeting some of these targets. What if you're taking oil samples? Right? If you're taking oil samples, you need to know that part of the sampling process is to ensure that we are meeting these targets. Right? So that's why sites will usually have some kind of contamination target. Now, when we are using our oils, I want us to imagine that this man here with his funny yellow hard hat is the machine Moses. Right, so this guy's going to come down from the mountain and he's going to tell you all about contamination control. And we're going to keep lubricants clean, cool, and dry. We are going to filter them when we pump them. And we're going to close lubricant containers when they're not in use. Bonus, prevention is way better than cure. And what I mean by that bonus one is basically if you can keep contamination out of the system in the first place, it's way cheaper and way easier than having to remove, through filtration or something similar, remove contamination. Right? So keep lubricants clean, cool, and dry. All right. This brings us to a question. Is new oil clean? Right? Comes straight out of the drum. Is it clean? This is a question that I have to ask a lot. Right? And I get various answers depending on what class I'm teaching. But it's one of my favorite parts of the course because it usually spurs a bit of debate. Now, obviously, in this context, I'm teaching through a screen, so I can't, I can't identify what your opinion is on the matter. Is new oil clean? Now, here's one where it's worth discussing. I want you to put yourself in the mind of an oil manufacturer. So your oil manufacturer, let's say they are making hydraulic 46 anti-wear, right? And they are making it for all sorts of customers. Some of those customers have incredibly tight cleanliness requirements. People that spring to mind would be plastic injection molding. If you're in the plastic injection molding business, you hopefully will know, but may not be aware, that oil degradation products and contamination of the oil will cause what we call silting of the valves, and it will cause them to stick, which means that the injection is not timed correctly, and you can result in product rejections. So cleanliness is very important for plastic injection molding, particularly like highly precise injection molding. All right. On the other end of the spectrum, you've got some of my customers in, let's say, the quarries of Outback Australia, where I don't know if you remember the scene from the Zoolander movie. Yeah, classic movie from 20 years ago now, where they're at the petrol station and they're like spraying petrol all over the place. That's kind of like what hydraulic hoses look like out there. A business like that is not going to benefit from any kind of cleanliness standard because, frankly, the oil is just going straight on the ground. They need to fix up their hose practices first before they look at any kind of contamination target. So going back to the oil company, what cleanliness standard do you manufacture to? It's an impossible question. because filtration and ensuring a level of cleanliness, that costs money. And which customer are you going to optimize for? Right? If we optimize for the plastic injection molder, we are cleaning our oil to a way finer standard than the quarry will ever need. And therefore, it's adding cost to the product. So the practical way that this is resolved is that most oil companies do not manufacture it to a cleanliness standard. Right? They just make the oil, and it is what it is. It's up to you, firstly, to define what new means, because new is different for every site. Okay, so you need to determine what clean is. That's the first thing. Right? The second thing is that sometimes the manufacturing process will vary. So they can't guarantee the cleanliness. In practice, you might say, well, hang on, my oil supplier, they have agreed to supply at a certain cleanliness. So what generally happens in practice is that they may test the oil, and if it doesn't already meet your spec, they send it off to a third-party contractor who actually filters and polishes the oil and then sends it to your site. So that's what happens in practice. And one of the other reasons why is because there is a bit of a chain of custody that oils can go through. So bulk product might get manufactured at the blend plant. It might then go into a truck to send to a distributor who puts it into a tank, who puts it into another truck, who comes to the customer's site, who puts it in a tank that hasn't been cleaned in 20 years. And every single time we transfer the oil, it just accumulates contaminant. So we've got to be very careful about this. So one of the things that we suggest, right, is considering whether bulk or packaged product is right for you. Right? Bulk, there's more transfers involved. It's a higher risk if you stuff up. Generally, it's lower cost per unit basis, though. Package, on the other hand, you're having to deal with a lot of manual handling, right? But at the same time, in theory, it's a cleaner product because it goes straight from the manufacturing facility to your site without ever having been opened. Nevertheless, when we receive products, we should always assume that they are not clean. We should always look at the paperwork. Is this the product the one that I ordered? If it is, maybe then we filter it to the standard we want and then we take it into storage. And one of the reasons why the receipt process for packaged goods is so important is because I've run into issues like the following. Right? Tell me which one of these is different. Now, you probably look at this and go, oh, and in a couple of seconds you go, oh, hang on, the one second from the left, that's different. But what's different about it? Right? It's not just that there's writing on the package, it's actually a different product. So all of these other ones are V220, and this one here is a T100. Now, in the Shell world, all their greases are called Gators. Actually, fun fact here, because I only found this out relatively recently, all the Shell products are named after shells, right? So, the most famous, of course, is the Helix product. Helix is a Helix shell. And anyway, Gatus is apparently a type of mollusk or something like that. Anyway, all the greases are called Gatus. So the number, right, this T100 or V220, remember that is the viscosity of the oil in the grease. It's still the most important property of the grease. The letter refers to the type of thickener. So in Shell world, V stands for lithium. Why V stands for lithium, I have absolutely no idea. Why it couldn't be L. And T stands for polyurea. So not only are these different viscosity greases, but they're also different thickeners. And yet they look almost identical. So checking the paperwork and checking what product is actually being delivered to site is incredibly important, right? Because you can imagine this would very quickly run you into compatibility issues. Now, another thing. Drums themselves. Drums are not what we call airtight. They breathe. Seems weird for an inanimate object to breathe, but imagine oil is sitting out in the sun, and let's say that it gets rained on because it's outside. Now the sun comes out and heats up the barrel. Now I've shown this the wrong way. The way I show this as oil expand. The oil doesn't expand. It's the air that expands, but it's difficult to show something that's invisible expanding. So just imagine that the air is being driven out by its expansion. So in the heat of the sun, the air is expanding and it escapes. Now we cool down. The air wants to contract. And it pulls a mild vacuum on that lid, but water is above the lid. And so the water gets drawn into the barrel. And that process happens over and over and over again every day. So as a result, we get water into perfectly new drums. Easy way to do that is store it inside, but that's not always practical on site. There's a lot of mine sites that just simply do not have the room to store hundreds and hundreds of drums. It would be a manual handling nightmare. So instead, what are other things we can do? We can put drum hats on. These enable the rain to just run off. But unfortunately, in very humid climates, we still get the buildup of a lot of condensation on the underside of that hat. Alternatively, we could store the drums on their side. Actually, if you take the MLA1 exam, this is the preferred method of storage. So they call it storing it on its side with the bungs at the 9 and the 3 o'clock position. In practice, what I have found is that most sites will not allow you to do this for safety reasons. Right? Obviously, they're concerned with barrels rolling. How else? We could lift one side of the drum so that the water sits on the lip. Right? Again, often not able to do that for safety reasons. And the other thing that we want to do is keep the drums off the ground if possible. Now, in practice, this sort of, bubbling out is shown in this video. So a friend of mine, Greg Romer, he took a video of this on a mine site in Australia, and you can see that air escaping from the drum. So this is that process in action. Pretty crazy, huh? Okay, another question for you. How long can I store oil? So now that I've received the oil and I've put it in storage, how long can it stay there? I get varying answers on this. For the most part, we generally will say about 5 years sounds about right. Most of the manufacturers will say about 5 years as well for standard mineral oils. So here's a bit of a guideline. 5 years sounds about right. If anything, in some climates that might be a bit conservative. The main thing is that if you store oils over the long term, especially in cold temperature climates, the additives can start to drop out a little bit. The main thing is check with your supplier. With storage of greases, remember I said make sure that the guns are depressurized so that we're not bleeding that oil out. And if you see a little bit of loose oil at the top of a pail, that's perfectly normal. In fact, if you got a clean spatula and stirred up that grease, the oil would basically go away. If you have large volumes of oil bleed out, that is a problem because it will dry out the grease. So try to store the grease cartridges inside, out of direct sunlight, and upright if possible. Okay, how can we prevent the cross-contamination of oils? Well, predominantly it's labeling and color coding. Every site that I go to has a slightly different system. You just need one that works for you. I personally like this one up the top left because it's very obvious what the product is. It's in bright colors. We've got exactly what kind of oil it is, the ISO grade, and then the actual name of the product. To me, that's perfect. But you guys can come up with your own system. It basically enables us to ensure that we are not cross-contaminating between products. Now, a bit of a story here. Honestly, I have a friend that I bring out on some jobs with me, and I think at first he was little bit reluctant to come because he sort of said, your job seems a little bit complicated. I've heard you talk about some of the different technologies that you maybe you're developing, and I don't know. But I said, well, no. He's a diesel mechanic by trade. I said, no. My job's actually pretty easy. You should just come along with me on one of these jobs. We were doing a lube survey at a site relatively close to where I live. I say relatively close. In Australian terms, that meant it was about a 6 or 7 hour drive. And I tried to explain to him, no, my job is actually very easy. And he didn't believe me. And when we got to site, all of a sudden a flip switched, right? And I think he realized that actually 90% of my job is basically telling people to clean up their room, right? Because the reality is that at most sites, the storage and handling situation is abysmal at most sites. That might not be applicable to you, but at most sites it is. And employing what we call basic 5S strategies. So it's effectively keeping things neat and tidy, right? Has incredible benefits for the lubrication program. Number one, what it means is that people take pride in their work. They recognize the importance of cleanliness. A well-ordered lube room, it speaks to something. In fact, not to get too philosophical, but I think Jordan Peterson. You may have your own opinions on his political beliefs and whatnot, but the core tenet of his original book, I can't remember, 12 Rules for Life or something, was basically, if you do the small things right, then the big things will take care of themselves, right? So that's what he talks about. What was it? Making sure that you're cleaning your room and things like that. He lost me at the lobster analogies, but the idea, and he's not the first to say this, right? There are lots of self-help gurus who will say, if you make your bed every day, you take care of yourself, you work out, you exercise, that shows a certain discipline, which then flows into the rest of your life, and you will therefore see life success, right? Those basic principles are true of lubrication programs as well, and you see it most clearly in the lube dispensing room. A very neat and ordered place is reflective of the fact that the lubrication program is held to a high standard. So when you go back to your site, I want you to keep that in mind, right? Is just doing the little things right, keeping things neat and tidy will then reflect in the quality of the program down the line. And sorry, that's me going to get off my high horse now. So the idea here is the basic skill that I need is to be able to effectively yell at my kids, right? So I practice that skill every day. But for a really good lube dispensing setup, you want something that's nice and clean, right? Here's an ideal dispensing room. It's clean, it's well ventilated. I get that it's not going to look like that necessarily at your site, but making sure you have all the tools available, that's what you need, right? And here's an example of what it can look like. This is at a mine site. And, frankly, it looks like you could eat off the floor. So we can do a great job of it. It's just that often we don't. And as an example here, like what would you change? Things like this is open to atmosphere up here. We're blocking the entrance to these aerosol cages. We don't have breathers fitted to the drums. There's not enough area here for spillover. There's no bunding. We've got rags hanging over. Hopefully we're not reusing those rags. We've got, there's a grease pail here which is completely open to atmosphere. So it leaves, and I've got to be perfectly honest. This dispensing room, this is kind of middle of the road. This is not even the worst dispensing room that I've ever seen, which would be far worse than this. And so again, just having a little bit of pride in our job makes a huge difference. And I said before that when we are dispensing, what do we want to do? We want to make sure containers are closed when not in use. And we want to make sure that we filter things when we pump them. Because I don't know if you remember, but going back to another slide, we said that every time we transfer the oil, we accumulate contaminant. This slide here. Right? And effectively, we double or we add 1 to the ISO code every time we transfer it. So by using clean dispensing practices, by filtering things as we pump them, we can reduce the buildup of contamination. Now, actually, this is where I get to use a prop. You may have seen one of these, right? There's a few different brands. This in particular has come from a company called ICAN. I tend to support those because I think they're an Australian brand. There's also OilSafe and Descase have their own containers. These are super, super useful, right? Really good, high quality, these are high density polyethylene dispensing containers. A couple of variations that you can get on them, right? So things that I would recommend. You can get variations where these have like quick connect fittings. So the standard way to fill these up, right, is to obviously open them up and then fill the dispensing container, chuck the lid back on, and then, hey presto, you're good to go. However, right, each time you open up the container, unless you are doing it in a very clean lube room, you are opening yourself up to contamination. So actually, in one of these pictures here, you can see that, or actually, you might not be able to see it. Let me see if I can zoom in here a little bit. You can see here that we are dispensing into the container, right, with a quick connect fitting. And that means that the oil is never exposed to atmosphere, right, where dust and particulate can enter the oil. So just something to keep in mind. All right, change of outfit. Sorry, I had something that I had to attend to. So we're going to restart here and talk now about different ways that we lubricate. So you may not have really thought about this too much, but there's basically manual and automated ways to either re-grease or re-lubricate. And we're going to start with the humble grease gun. Now, these here, right, these manual grease guns. Sorry, these manual grease guns here. So I'm holding one. They, you might look at that and you might think it's cute. Right? It's a thing of the past, a relic of a bygone age. I've been to plenty of mine sites, for example, where these no longer exist. Everything is now battery operated. The most popular ones tend to be the Milwaukee battery operated grease guns. But most of the small hand tool manufacturers have a version of that. Now, there's a couple of tricks to manual re-greasing. The first of which, right, is just to be aware that there is actually some serious danger to manual re-greasing. These lever-style grease guns and their battery-operated cousins can generally exert somewhere between 10 and 15,000 psi. Now, that seems like an awful lot, and it is. And the kind of thing that I generally will put to engineering managers is what other piece of equipment on site can generate 10 or 15,000 psi of pressure, and we simply hand that equipment to completely untrained people and send them out into the field with no training whatsoever. That, in many respects, seems ludicrous, if nothing else from a purely safety, health, and environment standpoint, let alone the implications for other things. So just the safety aspects alone should be a little bit concerning or alarming, let alone its potential to destroy bearings. So one of the criticisms that I have of the battery-operated grease guns, well, actually, there's two real main concerns. The first of those is that you don't get the physical feedback that you do from a standard lever-style gun. So again, if I've got one of these... oops, if I've got one of these manual guns and it's getting very, very difficult to push, that resistance is indicating that there's a blockage in the line, or perhaps that I'm pushing up against a seal. And that's feedback that you get with the kind of standard lever style gun. With these battery operated guns, you don't get that feedback, right? It's you can just hold your finger on the trigger and you can blow past bearing seals. You can absolutely over-grease something. I mean, I've talked to people who are literally re-greasing while not looking, and there's grease pouring out of a universal joint. It's just a bad situation. The other thing that happens is that grease can be dispensed too quickly with some of these battery-operated guns, whereby you don't get full distribution across the bearing, and so that can be challenging too. One of the common questions that I get a lot is, how much grease should I be using? And there's a variety of different calculations for re-greasing, and these same calculations would be applicable also to things like single-point lubricators. The thing about these calculations is that there are different methods. All the bearing OEMs, SKF, NSK, FAG, Schaeffler, they all have their own methods for calculating grease quantity and greasing frequency. And what you actually find is if that you put the same numbers and same bearing dimensions and speeds and loads and environmental conditions, if you do that across the different calculators, there's actually a substantial amount of disagreement between them. And that in itself is maybe a little bit alarming, because it certainly suggests that not all of them are correct. And so that's something that we've got to be careful of too, right? Just because we've calculated the correct amount of grease, there's no guarantee that that is the correct value. And so where there is a lot of value in a lubrication technician, or a fitter or an operator, whoever is holding that grease gun, there is a lot of value in being able to gather feedback as you are re-greasing. So, how does it feel when you re-grease? Is there resistance or not? When we are re-greasing, does anything happen to the sound signature? Does anything happen to the level of vibration? Does anything happen to the temperature, both before and after greasing? And that kind of feedback loop is what can help us dial in the correct volume for that particular application. So that's just something to think about as well. All right. So what else should we be concerned about? That the level of pressure that can be generated by these grease guns exceeds the vast majority of bearing seals. I mean, how many bearing seals or shields do you know that are capable of withstanding 10,000 psi? The other thing that you should really consider with a lot of these grease guns is the idea of calibrating a grease gun. So what you'll find is that I see a lot of PMs that are written, apply 10 shots of grease once per week. Well, not everyone and not every grease gun distributes the same amount of volume per shot. In fact, one of the best exercises you can do is get people to put, so you basically have a weigh scale and you tear it out so it goes back to zero weight. And then you get people to pump 10 pumps of grease onto the scale, take the weight and divide it by 10. And that will give you a good idea for how much volume per shot. The next thing that we want to do when we approach the grease point is to clean the grease nipple, because there is a good chance that what's the first thing that disappears on site? It's those little nipple covers, right? They disappear, and so it's important to clean with a lint-free rag, because otherwise we are simply forcing contaminant into the bearing. You then clean the end of the grease gun, re-grease with the amount of volume, replace the cap if there is one, or if not, put a little bit of grease on the end of that fitting to prevent further contamination. And then here's the key: depressurize the gun, because remember we said if you keep pressure, if that follower plate is constantly pushing on the grease will do its job and bleed oil out. So we don't want that. And then again, this bit of feedback: record the volume of grease that we pumped, record the date. Was there anything unusual? Is it hot? Is it making noise? Is it vibrating? As we re-grease, did that vibration come down? So these are all things that we should really be recording. Now, having said that, we might want to ask ourselves the question, why are we re-greasing? Because it's not always the case that we are re-greasing to lubricate. Say, for example, sometimes we re-grease seals. In some environments, we are re-greasing in order to purge contamination. This is one of the key differences between greases and oils, is that you cannot filter grease meaningfully. So you can use a mesh filter to strain out large particles, but the idea of filtering out submicron or single digit micron particles, you can't do that like you can for oil. So a lot of the time, if we find that a bearing is contaminated with particles or with water or process chemicals, the only way to drive that stuff out is to purge with grease. So sometimes we are re-greasing not necessarily to lubricate, but we are re-greasing to decontaminate. And that also changes the equation on how much volume we should be pumping. So the one thing that we don't want to get into the habit of is basically re-greasing simply by some kind of standardized rule. Either until you can't pump anymore or until we see new grease come out the other end. We don't want to be using those kinds of rules of thumb all of the time. And so that's the key that I would say with that. Now, how do you know if you've put too much or too little grease? That's another essential question. And the difficulty in diagnosing this is that over and under lubrication kind of look the same, right? So if you over-grease something, what's going to happen? I want you to think about being a rolling element in a rolling element bearing. So as you are trying to turn your way around the race, right, you are encountering resistance because of the amount of grease that's in the way, the amount of thickener. So the more grease is inside the housing, the more grease that's inside the bearing, the more it will resist. And so the other thing which is different about grease versus oil is that grease is an insulator. So it retains all the heat. It doesn't allow heat to escape. So over-greasing will usually cause heat buildup. Now, if I have excess heat, I will often get excess friction, potentially excess wear, and therefore more vibration. Okay, now let's consider the case for undergreasing. Well, if we undergrease, then we don't have enough lubrication. That generates friction, which increases temperatures, and as a result, we get vibration. So the consequences of both over and undergreasing can often look the same, and it can be very difficult to diagnose. One other thing which complicates this is that, on a lot of bearings, there may not be a relief port. We may not have a grease trap, which means if I continue to re-grease, that grease has got to go somewhere, right? It just doesn't vanish. And often where it ends up is in areas like, the electric motor windings. So something to be conscious of. So having said all of that stuff, how do you calculate the correct amount of grease? I've made it exceedingly complicated, right? We've got all these calculators. They don't agree with each other. Over-greasing and under-greasing, it's very difficult to tell which is which. So ultimately, we need to come to some way in which we can lubricate based on condition. And this is where we get into the idea of ultrasonics. Now, this here, I would say, is my personal favorite tool. So this here is the SDT340. There's another version that's called the Lube Expert. Just to be upfront, I'm a distributor of these in Australia, so I sell these. But I have been using these long before I became a distributor, just because I've always believed in the technology. So what can you do with these? The idea here is that, let's say, for example, I calculate the correct amount of grease, whatever that is. The correct amount of grease applied at the correct time is a process which keeps the current state of bearing lubrication constant. So if I am currently over lubricated and then I continue to apply the correct amount of grease, I will keep that bearing over lubricated. If I'm under lubricated and I keep applying the same amount of grease, I will stay under lubricated. So it preserves the current condition. And it's very difficult for us to know which one we're in, over or under. So this is the idea behind ultrasound greasing. So you can see that So basically, friction generates a kind of noise that is inaudible to the human ear. And when we are greasing, we are trying to minimize that sort of sound signature. And so the idea is we can pump grease and look for that sound signature to come down. And that suggests that we are starting to get into the optimal operating window. The biggest problem that we have with the sort of the basic ultrasound tools is that sometimes, right, people will, so there are basic ones which just give you a reading in decibels, and they will also allow you to, kind of listen to the bearing. So you get a pair of connected headphones, right? Here you go, and you can actually listen to the bearing signature. It's a process called heterodyning, where the SDT module actually takes the inaudible, what we call ultrasound, and makes it audible to the human ear. Okay, so you wear these headphones and you are waiting for the sound signature to get quiet. Here's the problem. Sometimes what I find is that the lube technician, who hasn't necessarily been trained in how to effectively use these tools, starts re-greasing, and there is no quieting. The bearing does not get any quieter. So they continue to pump grease, chasing, right, an eventual reduction in sound. Actually, what's happening is that they are already in an over-lubricated state, and as they are pumping, they are making the over-lubrication system worse. So these newer tools, like the SDT340 and the Lube Expert, really overcome this problem, because the way that these are designed to work is effectively on the panel, it will actually show you, right? It will instruct you pump 2 pumps of grease, 1, 2, and then it will listen to the bearing for you. And then if you need to stop, it will tell you to stop. If you need to continue, it will continue. And that is basically, if you like, an idiot-proof way of applying the correct amount of grease. And that's why I really like those tools. So it can tell you, let's say, for example, both at the start and the end, what's the sound signature at the beginning versus the end, and there's a reduction in that sound level. Or alternatively, if you have over-lubricated, it will tell you that as well. But you can see here, right? So if I zoom in a little bit on this one, right, look at that sound signature. The sound has only increased by 0.3 of a decibel before it recognized that you are in an over-lubricated state. And what that suggests is we've got to let the bearing run for a decent amount of time before we conduct another lubrication event. So hopefully that makes sense to you. So that's condition-based greasing. Then we get on to the idea of single-point lubricators. And I showed you one of these, right? So we'll get to that in a second. There are multiple types of single-point lubricators. These days, I would suggest that the vast majority look like the bottom right, these electromechanical styles. There are various ways. All of them rely on effectively the same principle, which is I have some volume of grease, right? And I have to push the volume of grease out the bottom using some kind of plate, right? So that plate pushes down on the grease and the grease comes out. A few things about single-point lubricators, right? So the first is the very basic ones are spring-operated. But of course, with springs, the dispensing rate can be influenced by back pressure. But also, spring tension is dependent on its distance. So it won't always apply the same amount of tension, same amount of compression to the grease. The gas or chemically operated ones, they are quite funky because they basically create, through a chemical reaction, they create gas inside of the chamber. That gas will then push on the piston, which pushes the grease out. But of course, gas pressure is dependent on temperature. So sometimes you get a bit of variation there. And just to skip ahead, basically everyone has gotten to those electromechanical ones, which is that effectively, so above this, there would sit kind of the battery module and the gear system, which pushes on this plate. So you can see in here, there's a plate that pushes down on the grease, and that then causes the grease to dispense out the bottom. All right, so what are some of the common issues that we might run into with things like single point lubricators? So as an example, as we are pushing down on the grease, like I said before, just the same as with the what do you call it? The manual grease guns. If we are continuing to place pressure on the grease, it causes some of the oil to bleed out. And so I've very commonly seen actually underneath here that you'll get a hardening of the grease. Sometimes it'll also happen in the lines as well. Another thing to note, another note of caution is that the amount of pressure that can be generated by these systems, it has a maximum value, and therefore the length of line, right, has to be known. So these different systems, they're actually rated to a specific line length and a line diameter. So I've run into issues, let's say for example, right, where the lines start to get a little bit longer. Let's say, here we go. Here's an example where you can see here that the lines are very long. These were actually designed for manual greasing. The ID here was probably in the order of about 1 millimeter. And so the reality is no grease is actually getting to the bearing because there is too much back pressure in that line. So that's one of the issues that I see with single point lubricators as they are used today. So, sorry, I wasn't showing that on the screen. Here you go. So here's an example, right, of really, really long, hard pipelines. So they've tried to do the right thing, right? From a safety perspective and from a ease of lubrication perspective, they're trying to do the right thing. But these long lines with very small IDs are meaning that there is too much back pressure there for a grease gun to exert. And so no grease is actually being received by the bearings. Now, if you needed confirmation of volume, right, there are new tools that are available. So there's an Australian company called Grease Boss. I don't know if you can see this here. So this module here is designed to sit under a single point lubricator and give you confirmation of the volume of grease that is actually being dispensed at the bearing. So now these are also very common in things like mobile centralized systems, which we will actually come to now, because with centralized grease systems, right, we have generally series and parallel systems. Not to get too far into the weeds, but effectively these series progressive systems work by firing in line. And that means just if one single unit blocks, they all block up. Whereas for the parallel systems, these can all be individually adjusted. And if one of these blocks, the rest continue to run. So that's centralized grease systems. What about gravity and wick lubrication systems? These are very common. You'll see them on a lot of old equipment. Just keep in mind that you can't turn off gravity, right? So it will continue to dispense, regardless of whether the machine is on or off. So you need some kind of shutoff to ensure that that doesn't occur. That's gravity and wick lubrication systems. I mean, very commonly we'll have things like splash lubrication systems. The main thing is to ensure that the oil level is not too high. Generally, we say sort of like halfway up the gear tooth. And how are you going to be recognizing that? It'll generally be through some kind of bullseye sight glass, right? So an example of that, this here is one of my kind of favorites. There's a company called Luneta that makes these. 3D sight glasses are really valuable because you can see the oil level from any angle. These particular ones also integrate an oil sampling port as well as a rare earth magnet for picking up kind of like iron and wear debris. So having something like this, right? I don't know if you can see it here, but it's actually, the reason it's called a bullseye sight glass is because it has a bullseye on the end of it. And so the idea is we are aiming to maintain the oil at a very specific height. All right, so that would be an example of a bullseye sight glass. You've got ring lubrication systems, which are designed to collect the oil from the bottom of the sump, right, and then kind of splash them up to the top of the casing. These rings, which just sit on the shaft, they're very effective at sort of lower speeds. Once you get up to high speed, you're having to look at a welded collar. And then we've also got things like centralized systems, which enable the use of filtration, and spray lubrication systems as well, where you can get a little bit more, let's say, accuracy with how we are dispensing the lubricant. So all sorts of different systems, both manual as well as automatic, as well as centralized, and knowing the differences is the key for you guys. For the people who are out there in the field, these are the important things to know. All right. Now we're going to talk a little bit about oil sampling. And let me just back up for a second from this rather scary picture. When we sample oil, I want you to think of this analogy, which is, and this is a common analogy, blood is to people what oil is to machines. So when we are taking an oil sample, the idea is that we are going to send this to the laboratory, and the laboratory will then test. So that's kind of like the pathologist. You know, you take oil samples, maybe you're getting your cholesterol tested, you send them to a pathologist, and then the test results will get sent to your doctor, and the doctor does the interpretation for you and tells you what action you need to take. All right, so that's the idea of an oil analysis program in summary. So what does that mean for you? If you are out there taking samples with something like one of these, you know, the sample thief, as we would call it, if you're out there taking samples, what is your role in this process? Well, effectively, you're the nurse, right? And what does a nurse do when they are taking blood samples from you? I just want you to think about all of the steps that the nurse goes through. They bring you into the room, and then before they do anything, they check your name and your date of birth. So what are we doing there? What are we doing when we are checking name and date of birth? Is we are confirming that we are taking a sample from the correct asset. And this is one of those steps that people kind of rush over in their haste to grab a sample. They forget to collect data correctly. And as a result, when the sample bottle reaches the lab, it is mismatched against a different asset, and as a result, the data is basically worthless. So that is a crucial step. What's the next thing that the nurse does? They clean the area, right? They prep it for sampling. We want to make sure that the oil sampling port is clean. And then what do? They get a new needle. They don't reuse equipment, right? They don't reuse dirty equipment. We are always using new tubing, new bottles, right? So this is the key. Then we go ahead and we take the sample, but we take the sample from the same location each time. So it's always taken from your arm, unless you're doing some other kind of blood sampling. So it's taken from your arm into a standard container, which is then, again, labeled correctly. It's then placed into a mail bag and sent immediately to the lab. And this is one of the steps that is missed in an oil analysis program, is that we take samples and we let them sit on the shelf for a really long time. And each day that these bottles sit there is just data, useful data that's just sitting on the shelf doing nothing. Now, why is oil sampling so important to the process? Why do you need to take clean samples? It's because, there's a couple of reasons. Number one, if we contaminate the samples, remember we said that contaminants in the air, which are invisible to the human eye, can be damaging to machinery. Well, in a similar way, if I leave the bottle cap off and allow contaminant to blow in, that is information that should not have been there. Right? You can think of that as noise. And that will make the sample invalid. In fact, there have been studies done by a couple of my customers where they looked into their overall oil analysis program, and they've discovered that between 25 and 30% of all the samples they send to the laboratory are invalid because of poor sampling practice. So your role in taking the samples is to make sure that this is done correctly. Right? The other reason we want to do it correctly is purely from a financial standpoint, because the way that most oil analysis programs are set up is that you pay for the bottle. So you pay up front. The bottle gets sent to you. You have already spent the money. You only get extract the value from that purchase when you sample correctly and have the lab test it correctly and give you insights, right? So that's the other sort of financial incentive for doing it. All right, so going back to our sampling theory, there is a correct way to sample blood. So think of yourself like a nurse. All right, when we take samples, that's an opportunity to detect, well, is there anything up here, right? Is the oil a little bit hotter? Does it smell funny? Does it look funny? Is there discoloration? If it's gone milky, that's an indication that we've got water in the sample. Has it gone dark? Dark is usually an indication of the oil cooking, that's oxidation, or else, if in the case of engines, diesel soot buildup. Does it smell interesting? Does it smell burnt? Does it smell acrid? Does it smell sweet? Most of the time, if you're taking a lot of samples, you'll start to recognize how the oils are meant to smell. Right? So we want to make sure that we are collecting this data, because you, as someone who is doing the lube rounds, are probably in a position where you touch more equipment than anyone else on site. And as a result, you are often best placed to know when something is wrong with the equipment. So you are often the first line of defense. So take with that what you will. The actual cleanliness of the bottle is important as well. So this is a slide that I teach on MLA 1. I like this one that was sent in by Mohammed, the idea of taking a sample in a bottle of Johnny Walker. Now, just to be clear, that's not all. That's like actually not the worst practice. If people laugh at it, because obviously it's a bottle of Johnny Walker, but actually, the reason it's probably done is because sometimes with turbine oil testing, you need to take larger volumes of oil, and sometimes people don't have 1 liter bottles that are new. So in a pinch, right? If you said, well, what's the best I can do? Well, glass is easier to clean than plastic, I would argue. So to get a glass bottle, what I would personally do is obviously decant as much of that volume as possible. So drink. Don't let that good bottle of Johnny Walker go to waste. Then you would, once you've drained out as much residue as possible, I would then actually use like a residue-free degreaser. So there are degreasers that you can get that basically evaporate on contact and they leave behind no residue. And if you've done that, that's about as clean as you're going to get a bottle. And that is probably a way to minimize bottle contamination. So it's probably not the worst practice in the world. When we sample, we effectively want to sample from something called the live zone. So we want to be staying away from the bottom of the container or the reservoir or the gearbox. And we want to stay away from the sides as well. So let's say, for example, if we've got a hard sampling tube here, right? So the idea here is that this length of tubing goes into the gearbox, right? I really like it when it's hard piped in because you can guarantee that you're taking the sample from exactly the same place each time. So that's what I really like, personally. So then you're obviously taking the sample from here. Now, keep in mind that this volume inside here, it has not moved since the last time you took a sample. So it's important to drain off probably about 5 times that volume. You might say 5 times is a bit of overkill, but the reality is, look at the ID of that. It's a very small amount of volume that you're actually having to drain off in advance. So that's the key, is try and take a sample as cleanly as possible. And I've got an example of best practice here. Right? So this is what we call the Ziploc method. So this video is showing a way to minimize contamination of the sample by using a plastic bag. So you actually have the bottle inside of the plastic bag, the plastic Ziploc bag, with the cap off, and then you screw the sampling bottle on top of the plastic bag and then use the piping, so the rubberized piping, to puncture a hole in the bag. The reason we do this is especially in very dusty environments, places like mine sites or quarries. If you're in the cement industry, there's a lot of airborne dust. And if we leave the cap off the sample for even a matter of seconds, we tend to find that a lot of dust ends up blowing into the container. And so sampling this way, this is the sort of the cleanest way possible. Okay. Now, this has become standard practice around a lot of mine sites in Australia. So, and they found it very effective at reducing the amount of sampling error. So, here is an example of that sampling error. So, this box here is from a company called Spectralytic that I work with, and they are testing basically real-time oil analysis. So, how do you basically testing in real time? And in order to validate that their technology works, they were having to test it against laboratory testing. And here you can see, well, the blue line, which is the lab testing, is a little bit more variable. So one of them's got to be wrong. It's got to be either the lab or the sensor. And the reason that we can have a fair bit of confidence that it was the lab which was wrong is because this is showing oil oxidation. And oxidation, or cooking of the oil, is a process that only gets worse. The only way it can go down is if you change the oil. So we know that there was no oil change, which means that these results here, those were bogus. So even in a trial where everyone has been worded up about the importance of clean sampling processes, even then, the sampling has caused errors in the data. Right? So imagine that this is what they are doing during a trial. Imagine how much worse it is generally in the field. And so we are trying to eliminate those errors where at all possible. Now, I would, if you've got a very high value asset or something which could incur a lot of downtime cost, then I could strongly encourage you to take a look at this technology. Yes, and the sticker price, it may look in relatively expensive, but in a lot of sites that I go to, it's an hour or an hour and a half of prevented downtime will more than pay for this kind of technology. So definitely worth a look. The final thing that you should be aware of, right, is that where you sample is just as important as how you sample. So for example, in a hydraulic unit, what is the thing that wears? It's generally the pump. So in a hydraulic unit, if I want to discover information about the pump wear, I need to take the sample here, after the pump, but crucially before the filter, because the filter could potentially remove the wear particles that I'm interested in testing. So we would take our sample here. Versus for a circulating system, right? Let's say, for example, this is a turbine with a few bearings, then it's the bearing wear that I'm interested in, and so therefore I would take my sample on the return line, right? So there are sort of like these little nuances to this about sampling and where it is important to sample. All right, and that basically brings us to the end of lubricant apprentice technician training. So hopefully over the last, I guess it's about 3 hours or so, you have learnt a fair bit about, the science of lubricants and lubrication, how they work, how important they are to reliability. If I could impress upon you anything from this session, it's that your job as someone who handles lubricants on a daily basis is incredibly important to machine reliability. It's incredibly important to uptime and incredibly important to the process. Right? What is it? Valvoline says oils ain't oils. That's true. Right? We need to treat oils and greases with respect because they are precision engineered instruments. How we store and how we handle them in real time ensures that they are not contaminated, and therefore we get maximum reliability out of our gears, bearings, hydraulics, and engines. Right. When we apply greases and when we apply lubricants, we're trying to do so in a precise way. We want to make sure that the oil level is precise. We want to make sure that the grease dispensed is precise. And you, as someone who is holding a grease gun, are the person who is in the best place to get feedback from the machine. Finally, when we sample, we want to be sampling as cleanly as possible, because the data that goes back into our condition monitoring programs is only valuable if the samples have been taken correctly. We don't want to confuse that data. So I really, really hope that you're able to take away something, a few nuggets from this last 3 hours. I want to, applaud you for sticking with it, because there are not that many people out there who now have the level of knowledge that you do. So I want to applaud you for taking the time and really putting in your best effort to do the best in your job and in your workplace. There's a lot of talk about AI and computing these days, but it's the likes of you guys who I think are really, making a difference in the world when it actually comes to industry. So thank you very much. And if you've got any questions, please reach out.